Come on in, everyone. Waiting for everybody to come in. I'm doing some stuff in the background as well. Okay, now it looks like I've got everybody here. Well, I got 12 of you anyways. I'm deferring everyone to the dates on the mastering. Anybody know that answer to that question? Let me look at it real quick, see if I can pull it up fast enough.
I was slightly wondering about that. It did say that the actual homework for chapter 22 is due tomorrow, I believe, but the conceptual for chapter 23 is due like
tonight or
like 31st.
31st. That sounds pretty correct. I did start last time with showing you how to do electric potential. So we are in chapter 23. So I would expect the chapter 23 concept questions to come up first, and then like 2 days later, the actual work questions. So 22 being first.
No, that's the weird thing. Both chapter 22 and 23's actual homeworks say they are both due by when it clicks over from Wednesday to Thursday. The conceptual for chapter 23 is due after it.
Okay. That might be a bit. Let me look at it real quick and see what I can do. I'm pulling it up right now.
I was looking at the syllabus and it said we have a test today, but I was thinking to myself, I don't think we do because you didn't say anything about it last class.
Yeah, I announced that I had moved it a week back.
Okay, cool.
So yeah, chapter 22 conceptual was due on the 24th, which was yesterday. That's reasonable because we clearly done enough of chapter 22, and 118 for 21, and then 23. I have 131 for conceptual. Okay, January 31st for conceptual. 21 was 119 for actual homework. 22 was 126, which is tomorrow. I think that's fine. Chapter 20. Yeah, okay. 20. Where's my 23? Oh, there's 23. So 23 is due on the 26th. No, that's not right. So the '23 conceptual was 131. So it should be after 131 that the 26 homework is due, or excuse me, 23 homework is due. So 23 homework, instead of being 126, I'm going to move that to probably January 2nd, your Tuesday, Thursday class. So yeah. And now let's look what 24 looks like. 24 looks like 9. Yeah. 25 is, yeah, that must have been some kind of typo. I don't even see 25. Oh, it's 25, 216. Yeah, okay, now it looks like it's reasonable. So what I now have is, and you can look at it yourself, but 118 conceptual 21 was due, 124 conceptual 22 was due, 131 conceptual 23 is due, and then conceptual 24 is 207. So all that sounds reasonable to me. And now I do the homeworks. I've got chapter 21 was due 119. Chapter 22, the homework is due tomorrow, 126. Chapter 23 is due on the 2nd of February, and 24 on the 9th of February. So yeah, that looks a lot better now. So thanks for bringing that to my attention. I clearly had a error on that. Regarding the test, I said it while you were talking, but I hadn't realized you hadn't stopped talking when I started the statement. So basically on my side, there's a slow click in the noise because we're having some bandwidth issues this morning. So I didn't hear most of what you said when you asked about the test. But yeah, there was a test. It was originally scheduled for last week. I told everybody that I moved it back a week But I did that just verbally, so y'all might not have heard it when I said it. It's now up and it's now available, and you have until basically 11:59 p.m. on Monday of next week to have your attempts done. I highly recommend that you, early as you can, like today, this afternoon, or whatever, take a couple pokes at the practice test and then go ahead and get one version of, or one attempt on your actual test done. That way, if you forget about it, you won't get a 0 on the test, or you won't have to use that 0 as your drop test. So that's what I'd recommend to do. And then, when you have more time between now and the weekend, then you can maybe, massage it, look over the old one a little bit, see what you missed, see what you can study to make sure you understand it better, and then take a second and maybe third attempt of test 1. Because I do want you to get a high score on that. That's what saves you for if you don't actually figure out how to learn so well by the midterm. You'll know in the midterm that you haven't been learning very well, because the midterm will be a very low score. So I'd much rather you have a bunch of high scores to counteract that when you learn that first piece of evidence. But really, I'd rather you just figure out how to learn right now, and hopefully most of you do. And that is normally the case. I normally have a good third to a half of the students do okay on the midterm. Not quite as good as they do on the practice on the online test, but still they do pretty good. So someone else had chatted something. Let me pull up the chats. I normally open them up, but I was looking at other things. So I had one question about chapter 23 homework. The homework itself is due tomorrow. Yes, we've addressed that, I believe, Jared. The second practice test is open too now, but the normal test isn't open. Well, let me look at that real quick just to make sure.
I was about to say, I don't see the online test in the drop-down tab.
Okay, I'm looking at that now. I got to go back to my modules. And if you go down to where it says practice tests, you should now see practice test 1 and practice test 2 is there. And then after that, okay, I see what's going on. It's available, but oh no, it didn't show that it was available. And the changes I literally just made are not showing. I literally just did that. Okay, let's do edit again. So test 1, it says TO1, chapter 21 and 22. The due date, which I changed, but it seems to have forgotten all of that. I don't know why, but it's just a crackhead. So that'd be January. And I'm putting January 31st at 11:59 p.m. And January 31st, 11:59 p.m. And I go to the questions, make sure they're there. They are. I'm going to save. And it should be available now in that section. Y'all see it?
Yeah.
Okay. So it's there. Don't click on it until you're ready to take an attempt, because like I said, each time you click on it, that's going to count as an attempt. But each time you take it, it'll be a different highest counts. Oh, I think maybe what I did was open test 2 by accident. No, that's practice test 2. That's cool. Okay. And it's still right now on my side, it's showing the wrong date. Let me check. It might just be that I need to refresh my screen.
No, it's still showing as the September date for some reason.
Okay, that is weird. It's showing the due date though under. It's still showing at September 10th date. Let me open that up and see why crap that's so.
Also, in looking at the test available time, I realized I need to email you a thing. So I'll try to get that sent to you shortly after class.
It literally did not take my date again. Okay, no problem. Just let me know. The date's still not changed. I'm doing it again now, which really should not be what I'm using my time for. I'm going to say save again. And now I'm going to go back to my modules.
Okay, now it's reading as January 31st for the due date.
Okay, that's weird. I literally had to do it 3 times to get it to take.
That's very odd.
Yeah, but it's par for the course. I've had I've had that happen a lot. It's weird, but yeah, it's like there's a gremlin. Yay, it says January 31st. Okay, I finally got it on my side. All right, now we've got that settled. Does anybody have any material questions, anything about voltage, that kind of stuff? Okay, well, I'm going to do a problem that I alluded to last time, because I actually took the ring and I gave you the result of the electric field and that we had gotten from chapter 21, but I never worked that on chapter 21. So I thought I'd work that for you today. And then I was going to then calculate the voltage for it and show you that we get it. We actually did the voltage part already, but I'm going to do that and then take it for and use that result to find the electric field above the center of a disk. So we're doing sort of some chapter 21 material, but it is related to chapter 23 because we're dealing with voltage. What I'm looking for right now is I'm trying to double check. Does anybody have their syllabus out right now for this class? I'm opening mine up in case y'all don't. We are 242 section D01B. And here's my syllabus. Oh crap, I did it again. I hit the stupid Microsoft Edge thing. Darn it. I hate that. I don't like Bill Gates. He's made me angry. I'll use the Adobe Reader. It will literally open up and I'll be finished reading it before the Microsoft Edge finishes. Opening. Yep. Adobe's already done. Still waiting for Microsoft Edge to open. Idiot. See, what I'm looking for is trying to see how I am on my pacing, basically. So I'm looking at that calendar and I'm trying to make sure whether I'm supposed to start chapter 24. I think today's another chapter 23 day, if I remember correctly, but I haven't checked it since like Friday. So I just want to make sure. Now's again a good time if you have any questions about concepts or anything like that. Today's the 25th. So we are expecting chapter 23, actually expecting chapter 23 to be started. I was looking at my notes. I did do with you guys that now let me double check that too. Geez, maybe I got everything confused. So the last day we met was not, well, yeah, it had to be Thursday. So that would have been the 20th. So I'm closing that. I'm looking at 242.
We started chapter 23 on Thursday.
Yeah, so okay, yeah, I'm looking at it right now. Yeah, I did the voltage. I showed you that the change in voltage is equal to the negative integral E dot dl. I showed you that the electric field can now be counted as having a units of volts per meter. Yes, and I showed you, I calculated the voltage and the electric field for a spherical conducting sphere of charge Q and radius R. And I graphed both the electric field and the voltage from R equals 0 to infinity. And then I did a neat little voltage problem for calculating the voltage at a point somewhere in the center of 3 charges. I showed you that once you have the curl being identically 0, that means the field is conservative. That means the integral from one point to another is independent of path. The closed loop integral is 0, and there exists a scalar field. So I showed you all that stuff. Then I did the voltage of the actual ring of charge and integrated that to find a specific voltage. Then I took the derivative of that with respect to Z, multiplied it by -1, and got exactly the electric field strength that we got in chapter 21. So yeah, so we did do that. What I'd like to do now is I want to show you that particular problem integrated, which again is something I had done on a video, but the video, something happened to it. It didn't work, so I didn't get to put it up on my Facebook page. So it'll be on this one anyways. But let's start off. This is PHY 242 D01B. This is on 125/22. I'm going to turn on my document cam because I'm sure y'all are seeing my bald head enough. So let's imagine for a second a scenario in which we have a ring of charge like this.
It's still not on the document cam.
Oh, thank you. Let's see it again. There it is. Okay. So we got a ring of charge. It's uniformly discharged. It's got a total charge Q and a charge per unit length lambda, which hopefully y'all now figured out. If this is uniformly charged, that means lambda's got to be Q over 2 pi times R, where R is the radius of this baby. Okay, so now I'm going to embed that in a coordinate system. That's going to be my z-axis up there. This is going to be my x-axis, and this is going to be my y-axis. And I'm really sort of using cylindrical coordinates, which you guys have covered. I'm certain y'all covered polar coordinates, right? Where you had r and theta instead of x and y. Cylindrical is that same thing where you have r and theta, but you also add z to it. Okay. So what I'm going to do is I'm going to imagine this is the beginning of a bit of charge dq, and this is the end. So this is my dq, and that's going to be equal to lambda times its length. Well, its length, this angle is theta, and this angle right here is d theta. So what that means is that length is r d theta, and that comes from our S equals r times theta equation from trig, where we introduced the radian measure. So dq is going to be lambda times r times d theta. And we know that Coulomb's law in vector form is just dq times rp minus rdq over 4 pi epsilon naught times the absolute, or excuse me, the magnitude of rp minus rdq. And that has to be cubed to account for the extra power up there. And that's what we're going to compute. Okay. So I want to know the electric field at some distance z above. So rp is the vector that points from the origin to the point. And can anybody tell me what that's going to be? Anybody tell me its magnitude, maybe? What's the length of that vector from the origin to that point that I'm labeling with the z? I'm not just labeling it. That is the actual z coordinate too, by the way.
I can't really see the.
Oh, you can't? Okay. Does it help now?
Yes.
So this
So
RP.
you said the point is z.
Yes.
So then it would be z the square root of z squared plus wouldn't it be like the square root of z squared plus r squared?
That would be, yeah, that you're actually jumping way ahead, but I'm just looking for the vector pointing to the p, but you're absolutely right. That would be the magnitude. So I want the magnitude of just RP. Well, its length is z, and it's parallel to the z axis. So I'm just going to call that z k hat. And here's the other part you were jumping ahead of. Technically, the way we're going to write RDQ, it's really weird. RDQ is just going to be R times r hat, which is technically a function of theta. Okay, that's a very special thing I want to point out to you in hopes of helping you in the future if you do go in the electrical engineering mode, or even if you go into computer engineering, you're probably going to have some electrical engineering stuff. But when you're doing, or if you have to take statics at all, when you're doing a coordinate system like the cylindrical coordinate system or the spherical or hyperbolic or parabolic, all those things, they have different unit vectors for them. But unlike I, J, and K, those unit vectors are functions. So when you have them in an integral, you've actually got to integrate them. Whereas the I, J, and K can just come out in front, whether you're integrating or taking a derivative. That's not the case with this other one. So let me zoom in for a second to this so you'll know what I'm talking about. This is zooming in of a cylindrical coordinate system, specifically just the polar part, because I'm getting rid of the z that's coming out of the page. You would say this is a point P, for instance, and its distance away is r, which our distance was capital R. Well, the way the coordinate vectors are in this thing is continuing exactly that direction, but exactly 1 unit long is r hat. Okay. And then 90 degrees in front of that is theta hat. Well, if you make a coordinate system here, there's my x-axis. There's my y-axis. You can see that this is theta. So this is theta 2. So as well, I mean, so r hat of theta, you can actually see the x component should just be the length of this, which is 1 unit times the cosine of theta. So that's cosine theta I hat. And then the y component is the length of this again, which is 1 unit times the sine of theta. So this will be plus sine theta j hat. So in fact, we now know what r hat is. It's cosine theta I hat plus sine theta j hat. So when I actually use that, I now have it in terms of I, J, and K, so I don't have to do any integrals of I, J, and K. Now, just for the record, even though we're not going to need this, theta hat is a function of theta, and I think you can see that the y component, or excuse me, the x component would be negative because this is theta. This is also going to be theta, so it's going to be negative sine theta I hat. The negative is because it's pointing that way. The y component is going to be cosine theta j hat. So a neat thing that you can see from this, if you take the derivative of r hat with respect to theta, you actually get theta hat. So that's something that'll remind you if you ever forget what theta hat is, but there it is. So now we've got what r hat is. So I'm going to actually rewrite this now as r cosine theta I hat plus r sine theta j hat. So that's my r dq. That's my vector that points from the origin to dq, which would be right there at that spot. Now, according to the formula, I got to calculate rp minus r dq. That's easy enough. That's just going to be z k hat minus r cosine theta I hat minus r sine theta j hat. And I also have to calculate the magnitude of rp minus r dq, which might look a little confusing here, but if you remember that you're going to take the Pythagorean theorem for 3 dimensions, which means z squared plus r squared cosine squared theta plus r squared sine squared theta, you can factor out that r squared and you get sine squared plus cosine squared, which is just 1. So ultimately it's just as I think it was Colby that said, z squared plus r squared square root is the answer. You can also just realize geometrically, this is r, the big R, and this is z. They're perpendicular to each other, so clearly it's the square root of z squared plus r squared. Does that make sense to everyone? All right, so now that we have that, we can put all this stuff in this god-awful, scary-looking formula, right? So I'm going to say E is equal to the integral of dE, which is, I'm going to go ahead and pull out my dq is lambda times r times d theta. The lambda and the r are going to come out in front. Okay, I'm also going to have a 4 pi epsilon naught out front. And then I'm going to have an integral of the d theta that's left from the dq. And then I'm going to have z k hat minus r cosine theta I hat minus r sine theta j hat. And even though they're after the d theta in physics, we sort of run fast and loose. So what we're saying here is this is still going to be integrated, even though it's after the d theta. We just don't care about where we wrote it because we know what we got to do, right? Now under here is going to be, in fact, z squared plus r squared to the, since it's got to be cubed, this was 1/2, so this will be 3/2. And lo and behold, our integral is theta, so that could actually come out in front as well. And I'm going to have to integrate this from theta equals 0 to 2 pi. Now here's the kicker. We know that cosine theta looks like this from 0 to 2 pi. And we know that sine theta looks like this from 0 to 2 pi. From that alone, you can see that this area plus this area is the same as this area, but opposite in sign. So we expect that to integrate to 0 because we're literally just integrating d theta, cosine theta, d theta, right? In other words, just cosine theta, d theta. I said d theta first, so it sort of like looked like I repeated it. Same thing here. I'm going to actually be integrating sine theta, d theta. Clearly, this is exactly the same as this, but this is positive, that's negative, so that's going to give you 0. So there's a couple mathematical reasons that it's 0, but let's look at it from a physics standpoint. If I have a charge dq right here, that's going to create an electric field that points in the k hat direction, also in the x hat direction, and also in the y hat direction. In other words, it's going to have it's be a three-dimensional vector that has a component in the x direction, has a component in the y direction, and has a component in the z direction. Now, if I go 188 degrees ahead of that, then I'll have a little dq over here that's going to have the same z component as this one does, but it'll have exactly the opposite x component and y component. So the x's and y's should actually cancel out just from the symmetry of the problem. So now I've given you a physical reason. If you wish to take the time, you can go ahead and integrate it and you'll get a mathematical reason again. I'm not going to bother you with that though. And the z is a constant and the k hat's a constant. So I'm going to say lambda r z k hat over 4 pi epsilon naught z squared plus r squared to the 3/2 integral of d theta 0 to 2 pi. I think you can see what's going to happen. I'm going to have a 2 pi r times the lambda, and then times the z, and then a k hat over here, and that'll all be over 4 pi epsilon naught z squared
Just like
plus
the page up a bit.
r squared. Oh, thank you. I'm glad you warned me on that. I was just getting ready to check. So that's the total function. Notice 2 pi r times lambda is actually just q. So my final answer is I'm going to write q z over 4 pi epsilon naught z squared plus r squared in the k hat direction. And that's my electric field. And that's just along the z axis, of course, but still it is along the z axis. So it has some generality. We can find it for any distance z away from the center of the disk, or the ring, I should say. Now that's pretty amazing, right? Now, last time we actually showed that the electric potential, which is really trivial, remember dV is just equal to dq over 4 pi epsilon naught r. So V is equal to integral of dV, which equals the integral. The dq, again, I'm just going to say is lambda times r d theta, and the 4 pi epsilon naught, and then the square root of r squared plus z squared is that.
Everything's not on screen.
It will go off screen again, sorry. So this is the formula, and I actually did it at the end of class last time, but it's so easy to do, I just figured I might as well do it again. dV is going to be dq over 4 pi epsilon naught r. dq is going to be the same dq I used up here, which was lambda times r d theta. And then the distance is just r squared plus z squared square root. So now I can get all this, and it'll say lambda r over 4 pi epsilon naught r squared plus z squared. I don't know why I'm writing r first and z second in this instead of the other way like I did before, but here we are. And that's the integral from d theta from 0 to 2 pi. So lo and behold, I get V is equal to 2 pi r times lambda over 4 pi epsilon naught. I'll write it the correct way this time. Z squared plus r squared, or the way that matches, not necessarily correct. And that's my electric potential. What we found was E is supposed to be the negative gradient of V. but this V only has a Z in it. So really that just becomes the negative partial of V with respect to Z in the K hat direction. So really all I got to do is take the derivative of V with respect to Z. And it's not even really a partial anymore, except if you're thinking about the R as a variable, but it's really not, because it's, you know, that's the actual physical feature. So I'm just going to take the derivative of this with respect to Z. And what I mean by this is, I shouldn't put it equals there, is I'm going to take the, this part right here is just Q. So that's Q over 4 pi epsilon naught square root Z squared plus R squared. Take the derivative of that, I get Q over 4 pi epsilon naught. The derivative of Z squared plus R squared to the negative 1/2 is negative 1/2 times Z squared plus R squared to the negative 3/2, because you subtract 2/2 and you get negative 3/2, and then times the derivative of this with respect to Z, that'd be 2Z. So you can see this 2 and this 2 cancels out, and I end up getting, this is just equal to negative QZ over 4 pi epsilon naught Z squared plus R squared to the 3/2. So that E, got right up here again, E is the negative K hat partial V with respect to Z. That negative is going to make that positive, so I'll get positive QZ over 4 pi epsilon naught Z squared plus R squared to the 3/2 in the K hat direction, which is exactly the electric field that I got doing the god awful integral way. Does that make sense? That's exactly like you might remember last semester we had potential energy was equal to M times G times Y, where Y is the distance above some arbitrary origin, Y equals 0. Well, if you take du over dy, you know you're going to get mg, right? Now, F, which is the gravitational force, is equal to the negative gradient of u. So doing that, I have to take this, multiply it by negative, but also since I took the derivative with respect to y, I'm going to have a j hat in front of it. So it's going to be negative mg j hat. Isn't that the weight or the gravitational pull on an object of mass m? It's mg pointing down. So that's exactly the same analog here. You can see that this has been true. This negative gradient of the potential gives us the actual force, because that was the force that was acting on the body, is a m times g pointing in the downward direction. So y'all see that parallel now, hopefully? Now, we can actually soup this up a little bit further and do another example. I can take, and now instead of having a ring of charge, I can have a disk of charge of sigma. Okay, I'm going to say the total charge is Q, but it's uniformly distributed over the surface such that sigma is equal to Q over pi r squared, where this is just r. Okay, this is my x-axis, this is my y-axis. I know that from the previous problem we found this E, so I could say DE is actually equal to, again, we're going to calculate some distance z above. We could say that's just equal to dq times z over 4 pi epsilon naught z squared plus r squared, like that. And then it's just a matter of integrating over all of dq. And actually this was like that. So maybe we can take that result that we got for the electric field for that ring, and we can add up a bunch of those rings to figure out exactly what the electric field is for a plate. Sorry, I'm looking back at something real quick. So all I have to do now, and yeah, that is lowercase r, because remember, we're going to divide this up into little individual rings like this. Now, if you cut one of those rings open, what you'd see is that basically, and you laid it out flat, it basically looks like this. Its thickness from here to here is dr. This inside is 2 pi r to there. And of course, we can pretend that's the whole enchilada, if you will, and use that as if it's going to be RD theta. This is actually the shape of it. It's going to be this 2 pi r. So we can actually find a surface area, a dq, is going to be a sigma times the area of this. So what I'm going to say is this area is 2 pi r dr, because the 2 pi r is this length, the dr is this, and it's a rectangle. You can tell we're off a little bit, but if you go to try to calculate what that is, it's really going to be 2 pi parentheses r plus dr. Okay, that's what that whole length is. And if you take into account these little triangles, it's going to be dr times 2 pi dr times 1/2. So you get in the dr squared, and dr is going to be taken as a limit as dr approaches 0. So you've got a square of a dr, which is infinitesimal small. So you can ignore that, and we're just going to say that dq is equal to, oh, I already wrote it there. dq is equal to 2 pi r dr, instead of including all that other stuff. So now I'm going to integrate this and say E is equal to the integral of dE, which equals the integral of z times sigma 2 pi r dr over 4 pi epsilon naught z squared plus r squared, like that. And that's all going to be pointing in the k hat direction, which we don't have to integrate, so that's kind of nice. So I'll get sigma times 2 pi z over 4 pi epsilon naught integral r dr square root z squared plus r squared. So we're really fortunate here because we can say, actually, let me write this in another color so it'll stand out better. Let u equals z squared plus r squared. And I keep writing that r as a big R. Sorry about that, everybody. Please make that change in your notes if you were copying around with it. Okay. If that's the case, if we actually let let u equals z squared plus r squared, then du would equal 2r dr. Or you could say dr is du over 2r. So I'm going to replace this dr with du over 2r. That r is going to cancel out with that, and I'm going to get an extra 2 coming down over here. I'm just going to call that 8. So I will say the integral is now equal to, and I'm keeping that as an 8 just because I like the 2 pi up top. That might be helpful later. over 8 pi epsilon naught integral of, now we
Not on
have,
screen.
excuse me. Oh, it's if I roll off again. So I'm now going to have u to the negative 1/2 du. We'll worry about the range of integration after I resubstitute z squared plus r squared in here. But the integral of u to the negative 1/2 is u to the negative to the positive 1/2. Yes, Edwin, divided by positive 1/2. So that'd be just basically multiplying by 2 again. So I'm going to get sigma 2 pi z over 4 pi epsilon naught. Notice the 2 disappeared because I had to divide by 1/2. And now I'm going to get this to the positive 1/2. So it'll be square root z squared plus r squared. And I got to evaluate that from 0 to r. And there's a k hat in there too. So I'm going to say 2 pi sigma z k hat over 4 pi epsilon naught. And now I'm going to take the r case, which is the square root z squared plus r squared, minus the 0 case, which is just the absolute value of z. Because it's got to be a square root. It came from a square root, so it has to be the absolute value of z. And that's my actual electric field. Now we can simplify this stuff like that. 2 pi can cancel out with this 4 pi and all sorts of good stuff. But the main thing is we got an electric field. Now, if I want to find the voltage of that, I could actually do the same process, but calculating it for a voltage, and then take the voltage of that and take the negative of the gradient of it, and I should get the same electric field back. That is really the goal. But now you've seen how we can actually take a Gauss's law for a disk and not actually use, or excuse me, Gauss's law, Coulomb's law for a disk, but not actually use Coulomb's law, rather use the result that we got from a previous application of Coulomb's law and add it up just using the geometry of the problem. So that's another chapter 21 type problem that you were supposed to be able to do. So I wanted to make sure I got that before the actual test came in, because I couldn't put that video up on YouTube, at least not yet. So now that we got that, and we now have the voltage, maybe we can figure out how to do something regarding the voltage of that disk. And that's chapter 23 material. And that's pretty much the last bit of chapter 23 that's all that relevant. Let's say, for instance, we want to calculate the, let's say we want to calculate the electric field, or excuse me, the voltage a distance z above a disk. So in other words, I'm going to attack the same disk now. I'm going to attack the same disk, but I'm going to do it using voltage. And maybe if we have time, I'll be able to take a derivative and multiply it by -1 and put a k hat on it and get the equivalent electric field, hopefully. So I'm going to put this disk of uniformly distributed charge in an XYZ coordinate system. Again, your book actually is you doing similar examples, but they're not necessarily orienting them the same way. Like they took this distance in a problem like this, they took this distance and called it X. I'm still calling it Z. And what I'd like to know is, what is V at this point P? Okay. So that's what I'd like to know. I'm trying to draw some squiggly P and it always turns out terrible. So y'all know what I'm talking about. Hopefully. This thing has a radius big R, it has a total charge Q, and it's got a charge per unit area, sigma equals Q over pi big R squared, like that. Okay. Now, what we know is that V, or dV, is equal to dQ over 4 pi epsilon naught R. What I'm going to use as my differential charge element is that disk. or excuse me, that ring like we did before. So that's my DQ. I'm going to say my DQ is in fact sigma times 2 pi r dr, like that. And of course, it has a radius r. Now, the distance away from that, of course, is z squared plus r squared. So now I can say v, which equals the integral of dv, is equal to the integral of sigma times 2 pi r dr over 4 pi epsilon naught. Again, the distance this is away, the relevant distance is z squared plus r squared. Kind of weird doing this, right? Thinking of that as a distance, but it's the only distance that makes any sense. So I'm going to say sigma times 2 pi out here over 4 pi epsilon naught out here. And now I'm going to take the integral of r dr over square root z squared plus r squared. This is a simple integral. We just did it before. So I'm going to say let u equal z squared plus r squared. Then du is equal to 2r dr, which means dr would be du over 2r. So I've got the r already there. I'm going to increase this again and say this is going to be sigma 2 pi over 8 pi epsilon naught integral u to the negative 1/2 times du. You can see the exact parallel of what we were doing with the electric field, only now we're using voltage, so it's a scalar and we don't have to worry about vectors and all that good stuff, which we didn't have to worry about too much on this one anyways, because we were integrating the stacks of rings basically. So now we're going to take this and we realize the integral of u to the 1/2 is u to the negative 1/2 is u to the positive 1/2 divided by 1/2. So again, I'm going to get sigma 2 pi over 4 pi epsilon naught. That's because I divided by 1/2. That got rid of the 8 and made it a 4 again. And that's going to be z squared plus r squared. And we're going to evaluate it from 0 to r. Okay. So this gives me sigma times 2 pi over 4 pi epsilon naught. Obviously, when I take the r case, I get, oh, this is supposed to be to the square root power, by the way. So this is going to be the square root of z squared plus r squared. And then it's going to be minus the square root of z squared, which again gives us absolute value of z. Okay. You can notice the difference here is we've got a z up here that's quite a bit different from this. So we can now look at this, and I think I got the same result they did. Let me see. 1/2, yes. Yes. Okay. I don't know. I seem to have lost an R somewhere. Oh, I know. Never mind. So yeah, this is the actual voltage that we get for this. This all works. We can replace that with just Z. We can now say the voltage as a function of Z, really, because we're just using that as a distance away. That voltage as a function of Z is, let's factor out a R squared from this for reasons that'll become obvious in a second. But if we factor out a r squared from this, then this will become r squared times z over r parentheses squared plus 1. And this one won't have it in there either. So that'll be z squared over, or that'll be z over r like that. And that r that's squared inside of there, that'll come out and become regular r, and I'll get 2 pi r times sigma, which is just q. So I'm going to say it's now q over 4 pi epsilon naught And this is now equal to the square root z over r squared plus 1 minus z over r. That seems about right. And we could actually go further than that if we really wanted to. We could actually do a binomial expansion and see that in the case of r being much bigger than z, which you can sort of see that already, r being much bigger than z, this goes to 0, and this just goes to z over r squared, or z squared over, or excuse me, z over r. And you'd end up seeing that it's basically sigma over, or excuse me, sigma over 2 epsilon naught. Any questions on that? All right. Well, I think that's quite a bit for doing the voltage on here. Let me see if there's anything else I really wanted to make sure I covered. Yeah, that's pretty good, I guess. There's a little bit of stuff about electric potential for a dipole. I'm not too worried about that. You will see those problems as you run along. I've already told you about the electron volts and how that's equivalent to energy. So we're essentially done with all this. Oh, okay. Now I could also, another way I could have done this is I could have taken, and figured out how R is going to be distributed, or Q is going to be distributed all over this. That will make this a little different, and I'll get a little, if you look at it, if you look at the example in your book ended up doing the exact same example I did, but that their result differs from mine because they're using a different, it looks like I think they're using a different value of Q than I did, because they're basically just using the fact that the charge per unit area is the same everywhere, so that 2 pi r times dr would be one area, and it would have a charge q. So sigma would be that little q over 2 pi r dr, but it'd also be that big Q over pi r squared. And when you relate that, you end up getting a 2 up here that cancels out with a 2 down here. So it will look a little bit different. I'm going to think a little bit more about that and see if I made some mistake. So this process seems to be pretty good, but I may have made a mistake when I did my Q. So I'll think about that and leave that be for right now. Does anybody have any questions on what we've covered so far? I don't know why I just did what I did with that thing. Everything looks right to me, but I know if I take the derivative of that with respect to Z, I don't think it's going to give me that electric field that I got back here. And maybe it's only supposed to in that special case where Z is much greater than or smaller than big R. That might be the problem, but I know this is correct. This electric field was correct. I'm pretty confident all this was right, but the only thing that's worrying me is this sigma exchange when I went in here and did all this. So just look at the example. If anybody finds a mistake, I will give them an extra homework problem, extra homework set of 100 for getting it right. So I'll make a spot in our module for you to turn that in. So maybe y'all can find my error, or if you can just start off from here, work it out properly, and point out what you think I did wrong. And like I said, anybody that turns that in, I'm gonna give you 100 for one homework set. I guess that's the best way I can make up for a boo-boo. All right. Now, the other thing we talked about before is we talked about this dipole moment. I want to make sure you guys are aware of this. This is something that's used over and over. Not only do they just do dipoles, let me turn the camera back to me. So in electricity and magnetism, we can treat distributions of charge sort of like Taylor series, Maclaurin series, those sort of things. Remember, you learned in calculus that there's such a thing as a Maclaurin series, and you could express, for instance, sine theta as theta squared over 2 factorial minus theta to the 4th over 4 factorial, so on, so forth. And cosine theta you could treat as 1 minus theta over 1 factorial plus theta cubed over 3 factorial minus theta to the 5th over 5 factorial, all that stuff. Well, it turns out you can make up electrical distributions in a similar way in like a series expansion. And what they do is they do it with poles. So you start off with a dipole, that means 2 charges. And then you can also do a 2 to the n pole. So for any power of 2, you can get a pole. So 2 to the 1 pole, 2 to the 1 power is just a dipole. 2 to the 2 power is a quadrupole. 2 to the 3rd power is a octapole, so on and so forth. You just keep on doing that. Well, what we discovered was if you take a charge, I'm going to show you this in a second, but if you take a charge negative q and a charge positive q and you separate them by some distance, so let's say this is positive and this one's negative and both of them have a charge q, okay, the electric field for this thing would point in the direction that a positive charge would go. So you'd say it point this way. What they define though is a quantity P, which is Q times D, where D is a vector, and D is in fact the vector that points from here to here. In other words, it points in the exact opposite direction of that a positive charge would be compelled to move around that thing. When we do that, that's the actual dipole. And the dipole has these neat things like torque, which we recognize as R cross F. Turns out to be torque is equal to P cross E. And the potential energy turns out to be negative P dot E. So representing this vector this way, if you had P this way and electric field this way, then this potential energy is at a maximum when P dot E is equal to P times E, which means cosine theta has to be 1. So when they're parallel. So what that tells you something about what happens. One, this P cross E would suggest it points down into the page. That's where the torque is. And we know that torque into the page actually causes something to rotate this way. So you see that with these two equations, a dipole moment tends to line with the magnetic field. And that should make some sense because the positive charge is going to want to go in the direction of the electric field. The negative charge is going to go in the opposite direction. So you'd expect them to come this way. And in fact, this reinforces it because you see that when this theta when that theta goes to 0, they're aligned and the potential energy is actually its maximum or minimum in case of negative. So that's something I just wanted to express to you. Your book does a new example with it. And it turns out, oddly enough, if you calculate that the actual force on a dipole and you consider distances really large compared to D, whether it be up this way or out that way, it turns out that these electric fields weaken by Z to the 3rd power. In other words, the distance away to the 3rd power. Coulomb's law gave us for a point charge that the strength of it decreases as 1 over R squared, but here we are looking at a plus and minus and they fall off like 1 over R cubed. That's a pretty neat thing. Turns out also the quadrupole is going to go off by even bigger factor of R and the octapole by a even bigger factor of R. If I remember correctly, it's like R to the 3rd, R to the 4th, R to the 5th, so on and so forth. So I just wanted to talk a little bit about that because we've been sort of I've been sort of leaving those examples to you to do within the book. And I guess that's pretty good for chapter 23. Chapter 24, we're going to start getting into capacitance now that we've covered voltage. I think that's next, yeah, capacitance. And we're going to be using that Gauss's law stuff over and over again. And when we do that, that'll give us more practice with Gauss's law, but it'll also show us a process that's sort of a real university level physics problem where you have to solve one thing to get something, you have to solve something else to get something else, and then you have to combine those results to get a final result. And that's really the most robust problem. And it's sort of the gatekeeper of this course. If you can't use Coulomb's law to get an electric field or Gauss's law to get an electric field, then use negative integral E dot dl to calculate the voltage, and then use C equals Q over V to calculate a capacitance that's basically just made up of the geometry of the capacitor, then you sort of haven't completed the course in a satisfactory way. So there's almost always a problem on my midterm and our final exam where you're going to have to go through that process. Use either Coulomb's law in that integral form to find an electric field, or use Gauss's law to find an electric field. Then use V equals negative integral E dot dl to find the voltage between two parts of a system, and then combine that result with C equals Q over V to calculate capacitance. When we get to magnetism, you're going to see there's an exact parallel where we can either use the law of Biot-Savart or Ampere's law to calculate a magnetic field. And then we can use the definition of flux, which is integral of B dot dA, to calculate a magnetic flux. And then we can combine the magnetic flux and the magnetic field to get the actual inductance of a device called an inductor. That's another gatekeeper type of problem. So it's a multi-step problem that's really a university level science problem that you guys got to be able to do. Okay. So that's where we're headed. I think this is good enough. Anybody have any questions on any past stuff? What I'm really wanting to do is jump back on and figure out what I did wrong with that, but I've already made it a extra credit problem for you guys. So I'll write here, find out what I did wrong, correct it, do it right, and turn it in. Now you can do all this in handwritten stuff. Try to write it neatly, and then take a photograph of it and load it up as a PDF. We'll say we'll do that by February 1. For extra credit. And now I'm going to take another color to box that off so you guys can see it. Okay, now be advised, I mean, this is not a hard problem to figure out what I did wrong. I just figured it out myself. But you can just look at the example in the book and that should give you a good feeling. Then you got to write it up. But I want you to take this opportunity to write it up like you actually close your book and solve it from here to here, getting the right answer with your book closed. Okay. If you have to stop because you forgot some step and look back in the book, that's fine. Continue that one, but throw it away when you're done. Go back and do it again until you can do it without it, because that will tell you really know what you're doing. I would say do both of those, like the electric field one I calculated back there, and then this one, and that would be excellent, excellent, excellent practice to make sure you understand what you're doing, as opposed to just are able to regurgitate answers or look up answers when you need them. So any questions on that? All right, well, I'm going to go ahead and let you guys go. We're jumping a little bit ahead, so we've gotten actually ahead more than I expected. I want you to use some of this free time that I've given you just twice now. I'm letting you out early. Well, actually, this one's only 3 minutes early. Actually, no, it's 13 minutes early. So I've let you out twice early. So I really want you to go to my YouTube channel and look for electricity and magnetism related problems to do on there, and see if you can't do them yourself without, after you've watched the video, stop it and then just try to solve it yourself without looking at the actual workout problem. And when you run aground, stop, watch the video again. And those videos, most of them are lectures, at least most of the time of them is in lecture form. So you only have a small part that you really have to pay that much attention to when you're doing the actual problems, but those are excellent practice for you. So I'll let you guys go, and we will see each other again on Thursday. Don't forget to do your test by Monday, and have a good day. I'll wait for the last person to leave before I leave.
Thank you.
Thank y'all.
Professor, thank you.
Thank you,
Quick question,
Enrique.
Professor.
Yes.
Chapter 23, is it gonna still be due tomorrow?
I think I just changed that, didn't I? Let's see. Hold on. So chapter 23 concept questions are due 131. Chapter 23 homework is due on 202, so February 2nd. So no, you have some time on 23.
All right.
Have a
Thank
good
you.
one,
Have a
folks.
great day.
You too. Anyone else?
Yeah, Professor. So it's just, I think I stepped out for a bit. When you talk about the test, what test you mentioned?
Oh, so this class, every two chapters, we're going to have an online test, and it's listed in my syllabus on the dates in the calendar. But what I did was I moved this first one, which was on chapters 21 and 22. I moved it to be due not this Sunday that just passed, but this coming Monday at midnight. So 11:59 p.m. Monday of next week, the online test is due. You get multiple attempts. I think I gave y'all 3 attempts, but you've got a limited amount of time, and each time you take it, it's going to be different questions. So, the multiple attempts aren't as helpful as they sound, but they are extremely helpful.
Got it. Okay, and you're supposed to see, it's just the answer is on my lab, right?
Yes, yeah, you got to do the homework in my lab, and those due dates are set up there. And then you have the online tests, and then come midterm, if we're back in the classroom, we'll just do that in the classroom. Otherwise, we're gonna have to do some other stuff.
Got you. All right. Thank you, Professor.
Thank you. Have a good one, Enrique.
You too.